Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chaturji, and welcome back to my channel. Today's video is part 4 of our series, Excel for IS456 Beam Design, Shear Stress Calculation and Analysis. If you haven't already, I highly recommend watching parts 1, 2, and 3 first to build a strong foundation for this video. In this installment, we'll be practically applying the IS456 shear stress formulas in Excel. We'll cover calculating design shear stress, tau V, nominal shear stress, tau C, maximum permissible shear stress, tau C max, and how to determine shear reinforcement, or stirrup requirements, using our Excel spreadsheet. This is the second in our series of DIY projects for civil engineers. A quick tip for our non-civil engineer viewers: while the terminology might be specific, feel free to focus on the numerical operations and apply the procedures to your own projects where relevant. Now, regarding the free Excel sheet, many of you have emailed requesting it directly. To receive your copy, please carefully read the description below this video for the instructions on how to send your email request and leave a comment on this video confirming you've sent it. Both steps are necessary. Once you receive the file, please acknowledge it in the comments. This process helps me, other viewers, and allows us to share and validate this knowledge effectively. Your cooperation is appreciated. Throughout this project, I've benefited from the free assistance of Gemini AI. A big thank you to Gemini for their support. If you find this video helpful, please like, share, subscribe, and leave your comments below. Now, let's move on to the next slide and get started with the Excel calculations. Now, we are on the Excel dashboard, and we are watching the same dashboard that I have developed for my last presentation. The bottom section of this design sheet is a newly introduced area for shear design calculations. I will be adding the relevant formulas and 2 drop-down menus to the corresponding blank cells. Say our ultimate shear force, VU, equals to 50 kN. Below this, under shear bars section, we are watching 3 columns: bar diameter, number of legs of the stirrups, and number of links. Presently all the cell values are 0. First I am considering 2-legged stirrups. Bar diameter equals to 8 mm. Number of legs equal to 2. Presently I am not considering any links, so value of the cell will remain 0. Below this, we have ASV. ASV is the total cross-sectional area of a single set of stirrups and links. Now I am considering the first option from formula box. Formula for area of each sets of shear bars, ASV equals to, open parenthesis, 0.25, multiplied by, pi, open parenthesis, close parenthesis, multiplied by, square of, dia _03, close parenthesis, multiplied by open parenthesis, legs, plus, links, close parenthesis. By copying this formula I am pasting to this cell, and we are watching the value of ASV is 100.53 square mm. By the help of Excel option, define name, I have provided name of the cells are dia _03, legs, and links, respectively. Now I am changing the formula in the formula box. This is formula number 2, and we are watching, the formula is, if, open parenthesis, n, open parenthesis, check underscore 01 equals 2, OK, comma, check underscore 02 equals 2, OK, comma, check underscore 03 equals 2, OK, close parenthesis, comma, OK, comma, check, close parenthesis. In this Excel formula I am providing the command, if, check underscore 01, check underscore 02, and check underscore 03, are OK, then write OK. Otherwise, write check. Now, look at the row 13. Here you will find 3 checkpoints for the flex URL design calculation or calculation for the bending stress in the beam. Name of these checkpoints are check underscore 01, check underscore 02, and check underscore 03. If we find all 3 checkpoints OK, then we can say our design regarding flex URL design calculation is OK. If we find our flex URL design calculation OK, then only we can proceed towards the shear design of the beam. Because in the shear design of a beam, percentage of the provided steel are in one of the main roles. So I am going to copy the formula from formula box and pasting the formula in cell A14. By the help of define name, I am providing the cell's name as check underscore 04. Next, I am changing the formula in the formula box. This is formula number 3, and we are watching, the formula is, equals if, open parenthesis, or, open parenthesis, check underscore 04, equals to OK, comma, check underscore 04 equals to, blank quotation, close parenthesis, comma, shear design, comma, check the above design, close parenthesis. This is a dynamic heading for the shear design. Summary of this formula is, if check underscore 04 is OK or blank, then in the heading we will find, shear design, otherwise, heading will be check the above design. Now by copying the formula from formula box I am pasting it in the cell, B14. Since check underscore 04 is OK, we are watching the heading, shear design. Now, I am changing the formula in the formula box and selecting the formula number 4, and you are watching the formula, equals to if, open parenthesis, n, open parenthesis, VUS equals to, nominal, comma, ductility equals to no, close parenthesis, comma, 1, if, open parenthesis, n, open parenthesis, VUS equals to, nominal, comma, ductility equals to yes, close parenthesis, comma, 2, comma, if open parenthesis, n, open parenthesis, VUS, greater than, 0, comma, ductility equals to no, close parenthesis, comma, 3, comma, if, open parenthesis, n, open parenthesis, VUS, greater than, 0, comma, ductility equals to yes, close parenthesis, comma, 4, comma, blank quotation, close parenthesis, close parenthesis, close parenthesis, close parenthesis. This formula will give us the types, such as, type 1, type 2, type 3, and type 4. Name of this F14 cell is case underscore type. In the later half of this presentation, A drop-down menu allows you to include ductility detailing in your calculations by selecting yes or no. Consequently, the VUS column will automatically indicate whether nominal stirrups or design stirrups are required. Now I am pasting the formula in this cell. Since the ductility and VUS cells are blank, we are watching the case underscore type as a blank cell. Now, I am switching over to sheet 3 to explain the case underscore type of this design. I have divided case underscore type of this design into 4 types, that you are watching. When tau c, max greater than tau c and tau c is greater than tau v and we are not considering the ductility detailing, then it is type 1. When tau c, max greater than tau c and tau c is greater than tau v and we are considering the ductility detailing, then it is type 2. When tau c, max greater than tau c and tau v, but tau v is greater than tau c and we are not considering the ductility detailing, then it is type 3. When tau c, max greater than tau c and tau v, but tau v is greater than tau c and we are considering the ductility detailing, then it is type 4. In the last column of this chart, we will calculate the spacing of the stirrups. Once again, I am switching over to the sheet, named as design. In the case of type 1 and 2, under the cell VUS, we will find nominal. But for the case type 3 and 4, we will find additional shear that has to be borne by the stirrups. Now, I am changing the formula in the formula box and selecting the formula number 5, and you are watching the formula, for basis of the design. Equals to if, open parenthesis, n, open parenthesis, check underscore 04 equals to OK, comma, or, open parenthesis, case underscore type equals 1, comma, case underscore type equals 2, comma, case underscore type equals 3, comma, case underscore type equals 4, close parenthesis 4, or function, close parenthesis, 4, and function, comma, VLOOKUP, case underscore type, comma, sheet 3. $A $2 to $C $5, comma, 2, comma, 0, comma, blank quotation, close parenthesis. 4. If function. This formula tells us, when check underscore 04 is OK, and case underscore type equals 2, 1, or 2, or 3 or 4, use VLOOKUP function, and in the VLOOKUP function, lookup value is our case underscore type, lookup array is the $A $2 to $C $5 of sheet 3. COL underscore index underscore number equals 2, range lookup value is 0 for exact match. Otherwise, keep this cell blank. Having completed row 14, we see that check underscore 04 is OK. Consequently, the dynamic heading displays shear design. Since the ductility and VUS cells are blank, the case underscore type cell is also blank, resulting in a blank basis of the design field. Next, we have to put the formula in the cells of row 16. Now, we're going to create 2 drop-down menus in cells A16 and B16. We've named these cells K and ductility. To do this, in the formula bar, we'll select formula number 6. As we know, we can increase the value of tau c by up to 1.154 times its original value, but this enhanced value should never be greater than tau c, max. We've divided this enhancement factor, or K, into 4 options, 1, 1.05, 1.1, and 1.154. Here, 1 means no enhancement. Sometimes, when calculating shear stress, it's logical to increase the tau c value. This K factor allows us to do just that. Now, from the formula bar, we select the values from 1 to 1.154. Then, we select cell A16. From the ribbon at the top, we click on Data, then Data Validation. Under the Allow section, we choose List. After selecting List, we'll see the source box. In this box, we'll type 1, comma and a space, 1.05, comma and a space, 1.1, comma and a space, 1.154. Our drop-down menu for selecting the K value is now ready. First, we'll select 1, which means we're not applying any enhancement to the tau c value. Next, we're going to create a drop-down menu in cell B16. To do this, in the formula bar, we'll select formula number 7. This drop-down menu lets us choose between accepting the recommended spacing of stirrups as per IS 13920, which deals with ductility detailing, or using the spacing we've calculated. To accept the ductility detailing spacing, we select Yes. Otherwise, we select No. Now, from the formula bar, we select the values Yes and No. Then, we select cell B16. Again, from the ribbon, we click Data, then Data Validation. Under Allow, we select List. In the source box, we'll type Yes, comma and a space, No. For now, we'll select No from this drop-down menu. Our next step is to find the value of beta in cell C16. This beta value is needed to calculate the value of tau c, which will allow us to find the designed shear stress, tau c, independently. In other words, to get the tau c value, we won't have to refer to Table 19 of IS 456. Now, in the formula bar, we select formula number 8. We can see the formula equals if, open parenthesis, check underscore 04, equals, OK, comma, if, open parenthesis, if, open parenthesis, FCK, less than or equal to, 40, comma, open parenthesis, 0.8, multiplied by, FCK, divided by, open parenthesis, 6.89, multiplied by, PT underscore PROV, close parenthesis, comma, if, open parenthesis, FCK, greater than, 40, comma, open parenthesis, 0.8, multiplied by, 40, divided by, open parenthesis, 6.89, multiplied by, PT underscore PROV, close parenthesis, close parenthesis, close parenthesis, less than, 1, comma, 1, comma, if, open parenthesis, FCK, less than or equal to, 40, comma, open parenthesis, 0.8, multiplied by, FCK, divided by, open parenthesis, 6.89, multiplied by, PT underscore PROV, close parenthesis, comma, if, open parenthesis, FCK, greater than, 40, comma, open parenthesis, 0.8, multiplied by, 40, divided by, open parenthesis, 6.89, multiplied by, pt underscore prov, close parenthesis, close parenthesis, close parenthesis, close parenthesis, comma, quotation mark, close parenthesis. Here, pt underscore prov represents the percentage of steel we've provided, which we used in our bending stress calculation. Let's break down this formula in simple terms. Step 1, check if, check underscore 04 equals OK. First, the formula looks at the cell named check underscore 04 and sees if it contains exactly the text OK. Step 2, if the first check is OK. If check underscore 04 does indeed say OK, the formula then moves on to a more involved calculation to figure out the beta value. Step 3, if FCK is less than or equal to 40. It asks, is the value in the cell named FCK less than or equal to 40? If FCK is 40 or less, it calculates an initial result using the formula, 0.8 multiplied by FCK, divided by, 6.89 multiplied by the percentage of steel provided, or pt underscore prov. If FCK is greater than 40, we fix the value of FCK at 40 Newton per square millimeter. In that case, the formula becomes 0.8 multiplied by 40, divided by 6.89 multiplied by pt underscore prov. Notice that we use 40 instead of the actual FCK value when FCK is greater than 40. Step 4, after getting this first result, whether FCK was 40 or less, or greater than 40, the formula checks if this first result is less than 1. If it is, then the beta value is set to 1. If the first result is not less than 1, the formula repeats the same calculation it did in step 3 to determine the final beta value. Step 5, if the very first check, whether the text in check underscore 04 is exactly OK, is false, meaning check underscore 04 contains something other than OK, then the formula skips all the complex calculations. Instead, it simply leaves the cell where this formula is written completely empty. The two quotation marks together tell the spreadsheet to put nothing in that cell. In simpler terms, this formula calculates a beta value, but it only performs this calculation if the cell check underscore 04 contains OK. The way it calculates beta depends on the value in FCK. If FCK is 40 or less, it uses one calculation. If FCK is greater than 40, it uses a slightly modified version of that calculation, where it uses 40 instead of the actual FCK value. Finally, it checks if the result of this calculation is less than 1. If it is, beta becomes 1, otherwise, beta becomes the calculated value. If check underscore 04 is not OK, then the beta cell will be blank. Now, by selecting the formula, I am pasting the formula to the cell, C16, and we are watching the value of beta as 4.735, which is greater than 1. Now, we'll select the formula number 9 from the formula bar, and we are watching the formula for the design shear stress, tau c, of the concrete. The formula is equals K multiplied by, if, open parenthesis, check underscore 04, equals, OK, comma, if, open parenthesis, FCK, less than or equal to, 40, comma, open parenthesis, 0.85, multiplied by, sqrt, open parenthesis, 0.8, multiplied by, fck, close parenthesis, multiplied by, open parenthesis, sqrt, open parenthesis, 1, plus, 5, multiplied by, beta, close parenthesis, minus, 1, close parenthesis, divided by, open parenthesis, 6, multiplied by, beta, close parenthesis, comma, open parenthesis, 0.85, multiplied by, sqrt, open parenthesis, 0.8, multiplied by, 40, close parenthesis, multiplied by, open parenthesis, sqrt, open parenthesis, 1, plus, 5, multiplied by, beta, close parenthesis, minus, 1, close parenthesis, divided by, open parenthesis, 6, multiplied by, beta, close parenthesis, comma, quotation marks, close parenthesis. Here, K is the multiplication factor for design shear stress enhancement. By copying this formula, I am pasting it into cell D16, and we are watching the value of tau c is 0.531. By the help of define name, we are watching the name of the cell is tau c. Explanation of the formula in simple language. This formula calculates the design shear stress capacity of the concrete, tau c. It first checks if cell check _04 is OK. If it is, the calculation proceeds based on the concrete grade FCK. If FCK is 40 or less, it uses that value in the calculation. If FCK is greater than 40, it uses 40 instead. The result is then multiplied by the enhancement factor K. If check _04 is not OK, the cell remains blank. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, start. Our next mission is to find out the value of calculated shear stress of the beam, tau v. Now, we'll select the formula number 10 from the formula bar, and we are watching the formula for the calculated shear stress, tau v, for the beam. B is the width, D_EFF is the effective depth, and VU is the maximum factored shear force in kilonewton. VU is multiplied by 1000 to convert it to Newton. The formula is, equals if, open parenthesis, check _04 equals within quotation, OK, within quotation, comma, VU, multiplied by 1000, divided by, open parenthesis, B, multiplied by, D_EFF, close parenthesis, comma, blank quotation, close parenthesis. By copying this formula, I am pasting it into cell E16, and we are watching the value of tau v is 0.542, which is slightly greater than tau c. By the help of define name, we are watching the name of the cell is tau v. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, start. Now, we'll select the formula number 11 from the formula bar, and we are watching the formula for the maximum design shear stress, tau c max. This value corresponds to table number 20 of IS 456. The formula is, equals if, open parenthesis, check underscore 04 equals within quotation, OK, within quotation, comma, if, open parenthesis, FCK equals 15, comma, 2.5, comma, if, open parenthesis, FCK equals 20, comma, 2.8, comma, if, open parenthesis, FCK equals 25, comma, 3.1, comma, if, open parenthesis, FCK equals 30, comma, 3.5, comma, if, open parenthesis, FCK equals 35, comma, 3.7, comma, if, open parenthesis, FCK, greater than or equal to 40, comma, 4, close parenthesis, close parenthesis, close parenthesis, close parenthesis, close parenthesis, blank quotation, close parenthesis. By copying this formula, I am pasting it into cell F16, and we are watching the value of tau C max is 3.10 Newton per square millimeter, as the selected grade of concrete is M25. By the help of define name, we are watching the name of the cell is tau V. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, start. Now, we'll select the formula number 12 from the formula bar, and we are watching the formula for VUS. VUS is the difference between VU and tau C multiplied by B and D underscore EFF. The unit of VUS here will be kilonewton. This value is relevant when tau V is greater than tau C. The formula for VUS is, equals if, open parenthesis, check underscore 04 equals within quotation, OK, within quotation, comma, if, open parenthesis, tau V greater than tau C, comma, VU minus, tau C multiplied by, open parenthesis, B, multiplied by, D underscore EFF, close parenthesis, divided by, 1000, comma, within quotation, nominal, close parenthesis, comma, blank quotation, close parenthesis. By copying this formula, I am pasting it into cell G16, and we are watching the value of VUS is 1.031 kilonewton. In simpler terms, this formula figures out how much extra shear force the steel stirrups need to carry. It first makes sure everything is OK, check underscore 04 is OK. Then, it compares the actual shear stress in the beam, tau V, to the concrete's shear strength, tau C. If the beam's shear stress is higher than what the concrete can handle, the formula calculates the extra shear force and tells you how much the stirrups need to resist, in kilonewton. If the beam's shear stress is not higher than what the concrete can handle, it just says nominal, meaning the minimum amount of stirrups will be sufficient. The division by 1000 at the end is likely just to keep the units consistent in kilonewton. Alright, after getting the value of VUS, there are some changes in our design table for shear stress. Now we can see the case type as 3, and in the basis of the calculation, clearly, tau C max is greater than tau V and tau C. Ductility detailing is not considered. Now, I am switching over to sheet 3, and we are watching the formulas for the spacing of stirrups, SV. First, follow the top portion of this chart. As we already know, we have 4 case types. Now, Let's take a quick look at the formulas down below, identified by serial numbers 14 through 17. These formulas are essentially telling Excel how to calculate something called S_V, which you'll see in column C. Let's break down one of them, say the one with serial number 16, which corresponds to case_type equals 3 as indicated in the if condition. You see an if condition at the beginning. This is like saying, if the case_type is 3, then do this calculation, otherwise, leave it blank. Inside the if for case 3, we have min. Min stands for minimum. It's telling Excel to pick the smaller value from a few calculations. These calculations involve things like b, the width of our beam, d_EFF, the effective depth, Fy, the yield strength of the steel, ASV, the area of the stirrups, and VUS, which is related to our VUS value. So, these formulas are basically ensuring we calculate the spacing of our stirrups, S_V, based on the specific conditions of each case type and that we use the minimum required spacing for safety. You'll notice that all these if formulas we just talked about, the ones that calculate S_V based on the case type and identified by serial numbers 14 through 17, I've already pasted them into the corresponding cells in column C, right here. That's why, for case type 3 in row 4, you are already seeing a value of 250 in the S_V column. Excel has automatically done the calculation for us based on the formula we entered. All these formulas and conditions, such as ductility detailing, I have explained in my PowerPoint presentation. Now, the value of this SV, we have to fit in our design table under the column with the heading spacing, SV. To do that, I'm returning to the design sheet. Now, to bring in the value of SV, I am changing the formula in the formula bar. We'll select formula number 13, and let's take a look at the formula, equals if, open parenthesis, check_04, equals, quotation mark, OK, quotation mark, comma, or, open parenthesis, case_type, equals, 1, comma, case_type, equals, 2, comma, case_type, equals, 3, comma, case_type, equals, 4, close parenthesis, comma, VLOOKUP, open parenthesis, case_type, comma, sheet 3, exclamation mark, $, A, $, 2, colon, $, C, $, 5, comma, 3, comma, 0, close parenthesis, comma, quotation mark, close parenthesis. This formula is almost the same as formula number 05, which we used for the basis of design. The only difference is in the column index. Here, the column index is 3, instead of 2. By copying this formula, I am pasting it into the cell H16, and now we can see the value of the stirrup spacing as 250 millimeters. Our dashboard is now ready for testing. Now, I'm going to test this newly built dashboard. Trial 1, test for maximum design shear stress, or tau C max. Since the value of FCK is 25 Newton per square millimeter, in this dashboard, we are observing the value of tau C max equal to 3.1 Newton per square millimeter, which matches table 21. Now, I'm changing the value of FCK from 25 Newton per square millimeter to 40 Newton per square millimeter, and we are observing the value of tau C max equal to 4 Newton per square millimeter, which also matches table 21. By changing the value of FCK from 40 Newton per square millimeter to 60 Newton per square millimeter, we are observing the value of tau C max equal to 4 Newton per square millimeter, which again matches table 21. So, we can say this dashboard efficiently reflects the change in the value of tau C max with the change in the FCK value. Trial 2. Test for design shear stress, or tau C. Logically, we can say tau C is the intermediate value between tau V and tau C max. Before testing, I am returning to the starting point of the design by changing the value of FCK to 25 Newton per square millimeter. Now, we are observing the value of FCK equals 0.531 Newton per square millimeter. Here, the percentage of steel provided equals 0.613%, and we are seeing the value of tau C equals 0.531 Newton per square millimeter. According to table 19, with respect to the percentage of steel provided, between 0.5% and 0.75%, and FCK of 25, this value should be between 0.49 and 0.57 Newton per square millimeter. Here, 0.531 is greater than 0.49 but less than 0.57 Newton per square millimeter. Now, I'm changing the value of FCK from 25 Newton per square millimeter to 40 Newton per square millimeter, and we are observing the value of tau C equal to 0.554 Newton per square millimeter. As per table 19, this value should be between 0.51 and 0.60 Newton per square millimeter. 0.554 is greater than 0.51 but less than 0.60 Newton per square millimeter. Now, I'm changing the value of FCK from 40 Newton per square millimeter to 60 Newton per square millimeter, and we are observing the same value of tau C equal to 0.554 Newton per square millimeter. As we know, with respect to the same percentage of steel, if we increase the value of FCK beyond 40 Newton per square millimeter, the value of tau C will remain constant. That's why we are observing the same value of tau C for M40 and M60 grade of concrete, which is 0.554 Newton per square millimeter. Hence, we can conclude that the dashboard's value of tau C is very rational. Now, for our trial number 3, I am changing the value of FCK from 60 Newton per square millimeter to 25 Newton per square millimeter. Trial 3, presently, we are seeing the K value is 1, which means we are not considering any enhancement in the tau C value. Our VUS value is 1.031 kN, which is marginally on the higher side. The design type is 3, with the basis of the design being tau C max greater than tau V and tau C, and tau V greater than tau C. Now, I am changing the value of K from 1 to 1.05, which means we are increasing the value of K by 0.05. As a result of this, the design basis has changed to nominal design, the case type has changed from 3 to 1, and the basis of design has changed to tau C max greater than tau V, and tau v less than or equal to tau c for stirrups. We are observing that the spacing of stirrups remains the same as before, at a rate of 250 mm. Trial 4. Now, I am including ductility detailing in this shear design by changing the option from no to yes. As a result of this, the case type has changed from 1 to 2, and the basis of design has changed to tau c max greater than tau v, and tau v less than or equal to tau c plus ductility detailing. For stirrups, we are observing that the spacing of stirrups has changed from a rate of 250 mm to 125 mm. Trial 5. For trial 5, first, I am changing the value of K from 1.05 back to 1, and the ductility detailing from yes to no. I am also increasing the value of ultimate shear, VU, from 50 to 150 kN, and we are observing the spacing of stirrups has changed from a rate of 250 mm to 160 mm. Now, I am changing the value of K from 1 to 1.154, and the ductility detailing from no to yes. We are observing the spacing of stirrups at a rate of 125 mm. I think this is sufficient to prove the efficiency of this dashboard regarding the shear design of the beam. And that brings us to the end of part 4 of our series on using Excel for IS456 beam design, specifically focusing on tackling shear stress problems. In this video, we've thoroughly tested the dashboard's capabilities in accurately reflecting changes in key shear design parameters like tau c max and tau c based on variations in the grade of concrete, FCK, the enhancement factor K, and the inclusion of ductility detailing. We've also seen how the dashboard dynamically adjusts the required stirrup spacing in response to changes in ultimate shear force, VU. Hopefully, this demonstration has provided you with a clear understanding of how this Excel-based dashboard can streamline your shear design calculations, ensuring accuracy and efficiency in your structural engineering projects according to IS456. Don't forget to like this video if you found it helpful, and subscribe to our channel for more insightful tutorials on structural design and analysis using practical tools like Excel. In the next part of this series, we'll be diving into checking deflection criteria of the RCC beam. Stay tuned. Thank you for watching, and we'll see you in the next video. Happy designing!